Okay, then it's my pleasure to introduce Professor David Cahen, who's a professor at the Weizmann Institute of Science in the Department of Fast Materials Interfaces. I don't remember what it's called now. He's also a professor here at Ilan University and a member of the Center for Nanotechnology and now a member of the Center for Energy. He did his undergrad, I guess, no, not undergrad, but his master's and undergrad at Hebrew University. He studied chemistry and physics. Then he moved to Northwestern University and studied materials science and physical chemistry, then came back to Israel for his postdoc on biophysics and photosynthesis. And I think he's been in optoelectronic materials and the chemistry of them and their physics pretty much ever since. I can say he is my personal mentor, so I'm very proud to introduce him today. He definitely has many academic descendants in Israel and abroad, both in academia with high-ranking positions and in industry with high-ranking positions. So I think he's been very successful with his career. One thing that I don't think people know about him, but if you look into his academic tree, his academic great-grandfather was actually Linus Pauling, and two of his academic great-great-grandfathers were Niels Bohr and Erwin Schrödinger. So quite impressive from the top to the bottom, all in all. And today he's going to talk to us about possibilities and limits for a bright solar cell future, a guide for the perplexed.
Thank you very much, Hannah, and thank you all for joining. So this will be a worldwide tour of where we are with respect to photovoltaics. As in nearly any area of renewable energy or alternative energy or sustainable energy, whatever we choose to call it, it's very often oversold, but also very often undersold because there are enormous interests working in certain industries that will remain unnamed. I have been involved in this since the 70s and have seen rises and falls of the area. Since the early 2000s, I have been working on it in terms to try to figure out what are the limitations and what are the possibilities. And I'm not the only one. I have been helped or have taken guidance from many people. Some of them are shown here, and more will be mentioned during the lecture. Most of the research that I'll talk about today is research that was supported in-house at the Weizmann Institute, either directly or via Minerva Center. So let's look at how many different animals we find in the zoo of solar cells. So the big bully is silicon, which is part of the family of elemental semiconductors that can be used to make solar cells. Then we have the inorganic compound semiconductors, and they can be divided, and we'll come back to that, into two, single crystalline or polycrystalline. There are the 3 5s, and then copper, indium, gallium selenide, known as CIGS, and cadmium telluride. These two are rather special in that they are polycrystalline instead of what we had until now, only single crystal materials. And the ones that are commercial are silicon, cadmium telluride, and CIGS. Then we'll talk a little bit about the new boy on the block, halide perovskites, which are inorganic or organic inorganic ones, but mainly an inorganic framework. From that point of view, they are very close to this group. Let me change the pointer to this group. And then there is a large family of excitonic solar cells, which is based on organic molecules or organic polymers, sometimes hybrid, organic, inorganic, and that was exemplified by the dye-sensitized solar cell and quantum dot solar cells. And actually, you will see at some point in the lecture that these have become very efficient, but they have become very efficient because we use now halide perovskites instead of lead chalcogenides, as was done before. These two are special in that they show a property called self-healing, which allows materials that would be expected to be unstable to actually be able to function for a long time under solar energy irradiation. Then we can divide into systems with and without concentration. One cell or many cells stacked, we'll come to that. Homojunction means everything is, for example, silicon or gallium arsenide, or heterojunction, like cadmium telluride, which is made into a solar cell together with cadmium sulfide or zinc sulfide. So quite a zoo. The zoo was founded in its modern form in 1954 at Bell Telephone Laboratories with single crystal silicon. The solar battery. That was the ad of Bell Labs at the time. Some 15 years later, gallium arsenide joined, first very slow, and nowadays it's the most efficient solar cell that we know for a single junction, but it is not really available commercially, even though it is the cell that on which are based those that are, for example, on the James Webb telescope. Silicon cells are the ones that power the Hubble telescope. And until 2018, everything in space that went to and including Mars used solar cells as a power supply until the big sandstorm in Mars killed one of the rovers. And now when you go on Mars, they don't use solar cells anymore. There is a big single polycrystalline divide. And these were the ones that reigned supreme. In the 60s already, we had cat tellurides, in the 70s, CIGS, and then in the 80s, organic photovoltaics. In the meantime, several others went into the wastebasket. And as you can see, I'll go back, this divide has essentially shrunk to the point where it has disappeared. Now, what are the fruits of all this very hard work in terms of the best solar to electrical conversion efficiency? Or we should maybe be a little bit more honest and say, what are the solar cells in the lab with the lowest loss? Because they are, if you compare them to the solar collectors on your roof that collect solar energy and to convert it into heat, they're pretty lousy. So this compilation, and you'll see several of them, is for cells that are at least 1 centimeter square. And I compare to 2010. So here's the leader, and it loses 71% of its energy, of the solar energy. It cannot convert more than 29% into electricity. Then the best silicon cell follows, and after that we get the halide perovskite lab cell, CIGS cat telluride, and then there are these two. If you compare, you see that the change, especially in organic solar cells, has been amazing, and that in halide perovskite is even more amazing. Because of this halide perovskite jump, the one in organics is often not really noted, but it should be. Even in the others, there has been progress, but you can see that these two technologies were already pretty mature in 2010, and therefore the progress has been slow. Mind you, this is 79 centimeters squared. The others are just 1 centimeter squared. Now it's possible to put one cell on top of the other, and that each cell uses a separate part of the solar spectrum, where the least energetic one will essentially take whatever is left. There, if you put three cells together, you can get to a loss of only 62%. If you use, and this is the champion today, 61 times concentration with 4 cells, you are nearly at the possibility of converting half of the solar energy. The theoretical limit is above 80%, and this is how far we've got until now. Again, the progress, especially here, has been quite significant, but it's based on this material. Let's go back to something about which big academic and especially industrial wars are fought. What is a solar cell efficiency? It takes into account the total sunlight power that hits the panel and the power out. Should be very simple. But as in many of these cases, the devil is in the details. In this case, for example, if I take a 0.023 centimeter square area cell, how do I know it's 0.023 centimeters squared? Is my ability to define that area of the level of microlithography? And often it's not. So we have to take that with a grain of salt. By the way, this comes from an amazing presentation by someone called Steve Burns, and I strongly recommend to remember the name. Now, if I take, and this is very important because it is the result, the outcome of a battle that raged until about 2008. And the battle was about what is better for a solar cell. Should we make solar paint that we put everywhere on the roofs, on the walls, that is dirt cheap, or make more efficient cells? Not just for publishing in a fancy journal, but for practical purposes. And the answer has been resoundingly the latter. Because if you replace a 15 by a 20% efficient solar cell, then the solar cell cost will go down by nearly 25%. Nearly all of this you gain. And why is that? Because there's something called balance of systems cost, as anyone who works on a device knows, or works towards something for a device. And all of those costs scale in proportion to the area. And so here I compare 2013 solar PV cost for the same modules in Germany and in the US. And most of the difference is in these soft costs. Some of it's the cost of money, financing, then there's regulation, then there's the frame, etc. Note, 0.83 out of 4.93. That situation has improved somewhat. That's where we are in the US residential. The yellow is what costs the module. That's several cells together. Everything else are additional costs. Some of it, yes, we can try to do better with inverters, with electronic control, so that we have to put in less safety systems so that they will not short. But especially these soft costs that we cannot really control are very important. For residential, much more than for very large scale. That's the US, and this is Germany. The costs are lower. But you see, only in the utility we get to 50% about of the cost is the module. And therefore, once you do this, this remains the same, this remains the same, and this remains the same, and this remains the same. And this is very important because it costs a lot of money. All you can, therefore, you can gain if you put in a more efficient system. Now, there's a limit. We cannot on Earth afford, in most cases, to put in the very fancy solar cells that the James Webb Telescope has. But if we can, by making, for example, a technology more mature, to go from 20 to 22% for an industry, that's critical. Now, why aren't those cells more efficient? And for that, we have to understand what's a solar cell, a little bit. So this comes from a popular way to depict a solar cell, and I took it from Eli Jablonowicz. There may be an earlier source. And it compares it to a water wheel. where how much of the rainfall that you try to use to turn the wheel, you can convert, in this case, into mechanical energy, depends on the flow and the pressure. And the pressure is then equivalent to the voltage and the flow equivalent to the current. Now, there are several possible conditions for such a water wheel. You can open the tap completely, and then there will be a lot of current, but very little pressure. As a result, the water wheel will not turn very much. Or you can leave it open a little bit. You have a lot of pressure, but very little current. And therefore, anyone who uses this, and this has been known since times immemorial, you take an intermediate position. And that's the same for the solar cell. And we'll come to that in terms of the electrical behavior of this electronic device. A very general way of looking at it is that I have a system which I can illuminate, and as a result, I will create what are called electron-hole pairs. I take an electron from its bonding to non-bonding or anti-bonding, from the valence band to the conduction band, for chemist HOMO LUMO, and I keep them preferably in a place so that there will be a reasonable density of them. And I supply only two ways out, when for the holes and when for the electrons. What is really happening, here the electrons flow out, and here the electrons are injected, but we call them holes, missing electrons. Why is this important? For two things. A solar cell doesn't require a p-n junction, for those of you who know what that is. That's the popular electronic device. And the second thing is to sing the praise of C.P. Tang from Rochester, who, while working at Kodak Research, figured out the importance of selective contacts. Until the late 70s, early 80s, when he did his work, we didn't realize that. Now, if you look at the current versus voltage, by the way, Tang got the Wolf Prize. If you look at the current versus voltage of a solar cell, you can first look at it as in the dark, and then it's like a diode. So the current is here, no current, and then it goes up. It's a rectifier. If we shine light on it, then we get the red behavior. And this red behavior tells you immediately three things. In this quadrant, I am converting energy. In this quadrant, I am injecting energy, and I get, if I make my device correct, a light emitting diode. And a good solar cell will be a good light emitting diode. Here, I have a photodetector. It's not the only one, but it will be act as a photodetector. So this is where I have a solar cell. And this is the current when the tap of the water is completely open. And this is the pressure when the tap of the water is completely closed. Open circuit and short circuit. And then there is the fact that I cannot just take this current times that current because it's a diode. And therefore, I get less than the product of the current times voltage as my power, and how much less is expressed by the fill factor. This is the maximum power rectangle. Those are the three important quantities that determine the behavior of a solar cell. So we have short circuit, open circuit, and the optimal maximum power. Here they are, open circuit, short circuit, and the optimal working point, which is expressed in what we call a fill factor. Now still, okay, we understand a little bit how solar cells work, but why are they so inefficient? And that's because we lose most of the solar energy as heat, or we lose it because we can't use it. And that's shown here. This is a p-n junction, which is illuminated. So this is the conduction band, the valence band, and I bring in a photon, and if the photon has enough energy, then it can kick an electron from here to here, leaving behind a missing electron. In this ensemble, that's the formal definition for a hole, and an electron here. Now, the photon will generally not be exactly the difference between the valence and the conduction band in terms of energy. It'll have more, or it has less. If it has less, too bad, we lost all the energy, goes to heat. If it has more, what happens with this and that? Energy. And under all normal circumstances, we lose it. We lose it because of thermalization. There's a very active field of research that tries to find ways to use it, so-called hot electrons. So high energy photons, partial loss, low energy photons, total loss. These are the two most important losses in a solar cell. That gets you already very quickly to 40%. And the rest I'll give you now. So this curve is as a function of the photon energy, and in this case, the band gap. In other words, the energy, the minimum energy that the cell can use to take an electron from the valence to the conduction band and therefore activate the photovoltaic effect. And this is the current when I am putting the cell on short circuit, and it's ideal. So I am assuming every photon that is absorbed by the system gives me an electron that can flow in the circuit. And so you would get at nearly zero band gap, theoretically, to over 70 milliamps per square centimeter. And this is naturally taken according to the solar spectrum, AM air mass 1.5 global, for those who know what that means. Let's take a system where this is the threshold of absorption, the band gap of my semiconductor that determines how this solar cell works. So that means I can immediately see I can never get more power out than the product of this equivalent voltage, which will be the band gap without the electron. I divide by the electron charge and I get voltage. And this current, that's the green rectangle. But there are two losses, because I cannot use any of this because the photon energy is too small, not absorbed. And this one, this is the extra photon energy that I lost. By the way, this comes from a very nice paper by Louise Hurst and Nat Eakins-Dorms. Then we can look at it a little bit further. And in this diagram, which comes from Thomas Kirchhardt, I have again my p-n junction. And I now say this is my first process. I take the electron from here to here. Then I get the thermalization. And then I lose some energy when I collect the electron. So, and they have different time scales. We'll get to that. So already when the two we have seen here, which is the thermalization. And naturally here, I did not show all of the photons that are not absorbed because they have too little energy. Now there are more losses. And what are those? One is called photon entropy. It's a thermodynamic loss. It has to do with that the Earth intercepts only a very small solid angle from the solar energy. If you look at the sun as a disk, then most of it passes by Earth. That means that there will be, and the re-radiation of the solar cell, for example, under open circuit, when it's not converting any energy into electrical energy, will be in all steradian 180 degrees pi steradian angles. So I lose a factor of 46,000 in terms of entropy. And it's easy to calculate that at room temperature is about 0.3 electron volts. I can gain it back by concentrating. Then there is a Carnot factor. Even though this is a system that's really in steady state and not in thermodynamic equilibrium, Sadiq Carnot still reigns, and I lose a little bit. Because I can look at the system as the sun 5,800 Kelvin, and we luckily only at 300 Kelvin. Now you can be a smart ass and say, since these are thermodynamic losses, I go to 0 Kelvin and then I get a very, very efficient solar cell. There's even a paper recently in a very respectable, supposedly, journal, which says that they made a cell and they cooled it as if no one had done it before, and it became more efficient, and therefore it's very useful, very good for space. They naturally forgot that the main problem for solar cells in space is thermal management, and they only work when they face the sun. Otherwise, they're not converting anything. Then there is the emission loss, and I already noted it, or at least referred to it, that if the cell is at open circuit, it's not converting any of the solar energy into electrical energy. And so what's happening with the energy that hits it? Part of it will go to heat, but everything else will be emitted as light. And we'll come back to that. And that will decrease how much will be emitted as light as I go away from open circuit and start collecting current. So when I get my tap just at the right position to get the optimum power. And finally, I have electrical power out. So those are the main losses in a solar cell. We can first look at how the solar cells that we talked about do in terms of their theoretical current that they can give, which is the green line here, instead of the one that I showed before, but it's the same line, same calculation. At short circuit, there are the blue dots, and at maximum power for the existing best solar cells that, that I gave you before in the table to make an impression how inefficient solar cells are. So see, silicon is amazing. It has nearly 99% or at short circuit of all of the photons that can be absorbed, converted into electrical energy. Gallium arsenide less so. Telluride, which nowadays is telluride selenide, is doing better. And here is the halide perovskite and the others. Now, to put things in perspective, we're talking here about milliamps per square centimeter. The steady state equivalent current in terms of electron transfer rate of natural photosynthesis is less than 10 to the minus 2 milliamps per square centimeter. It's not on this plot. Now, I did a dirty trick here because there is a big difference, a huge difference between the solar cell and photosynthesis. Because in photosynthesis, I also store the energy. And in solar cells, I don't. And that's why solar cells need separate storage. I can also look at something, the external quantum efficiency, which essentially is the current as a function of monochromatic illumination. And ideally, I would like it to be from wherever the sunlight starts to reach till the cutoff to be a rectangle. And the best cells get close to it. It's difficult to see maybe in this very busy picture, but the champion is someone called gallium indium phosphide. But it has a very high energetic cutoff. Now, there are cells that are significantly worse than others. And they are, in particular, the organic photovoltaics, although it has improved, and amorphous silicon, which used to be commercial, but now is phased out. If we take a close-up of these cells, we see that here is gallium indium phosphide. So yes, it absorbs only a few photons, but it shoots up very sharp. And compare that to something like this organic photovoltaic cell. And here are the others, gallium arsenide, and this is one of the claims to fame of the halide perovskite, that it has a very sharp, what we call cutoff or turn on in terms of the current as a function of photon energy. So this is a short circuit. Now there is a model, and it's called Shockley-Queisser model after the two people that published the paper in 1961 in Journal of Applied Physics. By the way, the paper is an example of something called the Sleeping Beauty, which means that it lay dormant mostly for 2 decades. Generally, Sleeping Beauties you find in mathematics. There's a very nice paper on it in Proceedings of the National Academy. The model says we consider a photovoltaic effect in terms of something called detailed balance. And like the sun, what goes in does come out. The number of photons that goes in should equal the number of electrons that go out, plus the number of photons that go out. If you didn't pay attention, you'll say, wait a while, Cahen, photons out? I have a device that's supposed to convert photons into electrical energy. Yes, but as I explained to you, some of these electrons will actually be emitted. Because I'm not working at short circuit, because then I won't convert energy. The assumptions are that this happens on Earth at room temperature for a single absorber, single junction. And I'll come back to those assumptions. So here is the theoretical limit with a modern day solar spectrum that we know. And here are the best performing solar cells where all are 1 centimeter square except gallium indium phosphide, because it has not been made in such area. And you see that we're not doing that fantastic. There's quite a bit of difference between the theoretical maximum and where we are. These are the leaders, and these are the second runner-ups, where especially this one is trying to inch its way up. You generally will hear about, but these cells are already nearly 20% efficient, 26% efficient. Yes, but here we're talking about 1 centimeter square. And these are the other ones, where the one that to watch is this organic photovoltaic cell. And this DSC is a recent development, actually, which is quite surprising. Let's go back to the timescales, because I gave you a time scale without any indication which times we're talking about. So we look at a solar cell in terms of its the band diagram. This is the valence band top, conduction band minimum. And this is the band gap. And we do as if we can put in the same scheme its connection to something that measures the external voltage that we apply or that we can measure. This is energy. So we shine photons. They are unused photons, and then there are absorbed ones. Those are the ones we're interested in. They do their thing, and we get this excitation and thermalization, and then finally collection. Emission happens at about the same time scale as the excitation, a little bit slower. If we now put numbers here, we have the loss of unused photons and the emission generally in the femtosecond time scale, and the collection will be generally microseconds. It's the thermalization in the middle. Those are the time scales that are important, and they're generally well separated, the nice solar cell. So 1, 2, and 3, 1, 2, and 3, and we saw this before. Now, it won't always happen like that. I have excited the electron to here. It can indeed do 2 and 3. Fine, I've collected it as electrical energy if I'm not at short circuit, but it can also return and emit light. And this band-to-band transition is the desired one. But if I have imperfections, structural or impurities, then there might be, and often are, levels in this band gap, which is also called the forbidden gap. So it's not forbidden anymore. And that kind of recombination is disastrous for a solar cell. So I try to minimize it. I can compare it to, again, my bucket of water. If I have leakage from the side or from the bottom, where the bottom leakage would be like this, which we call recombination in the bulk. Now the side leakage is more difficult because I'll have these levels also at the surface because, as you probably know, Wolfgang Pauli, the Pauli principle, is quoted as having said that God created materials and the devil created the surface. Let's go back to the Shockley-Queisser model with these pictures that I went through before. The assumptions of the model, and their assumptions, because it is a model, is A, that the absorption is a step function. There are some problems there. How do we define experimentally the band gap? It turns out not to be something that has a single answer. And a smart colleague, Uwe Rao, has devised a practical way to get it from the performance of a solar cell. It will be an effective gap. Then there's a possibility of reflection and lack of transparency. All of these affect the first assumption, because the assumption is that I'll have a perfect step function, on, off. The second one is that one photon gives one electron hole pair. Now there can be parasitic absorption, where the photon is lost, but doesn't go into the photovoltaic effect. Furthermore, I can lose it after the work has been done and the electron and hole are there, but I can't collect them because, for example, the recombination that I talked about. Then there's a thermal effect, which actually has to do with the photon entropy effect that I talked about. If the cell heats up, then there's radiative recombination beyond the one type band-to-band that I want. The first one is the Auger, which some of you know should be called Auger-Meitner effect. Then, yes, there are defects in the material because every material has defects. The question is, are they at the level that they are significant for my cell behavior? And then surfaces, and I talked already about Pauli's definition and interfaces. And finally, there is this contribution of time that I have to be selective. I have to only, when contact, collect the holes, and the other contact, the electrons. And in terms of electrical engineering language, it's resistive and shunt resistors. So all of these will reduce the efficiency of a solar cell in the real world. Now there's the other way around. Can I go beyond the limits of the model? And then in order to get the headline, we say we broke the Shockley-Queisser limit. You didn't break any limit. You just violated one of the assumptions. And therefore the model is not valid anymore. But that makes it worse headline. So can we go there? And yes, and this is a very active area of research. And the first one is to stack the junctions, because then it's not anymore one step function. Then I'm absorbing with more than one step function. Then there's the possibility of what's called upconversion. I can take two photons and make them into one. This happens in nonlinear materials, only at rather high intensities, and therefore was never considered practical. But in the last decades and a half, triplet annihilation has shown that it might actually become practical. And this is something that happens in organics. And then there are intermediate gap ideas. And until a few weeks ago, I would have told you it's impossible. But a few weeks ago, I was exposed to the first system that might actually make it practical. That means I have my band gap, but I have a level in between. And I can, in that system, go from here to here and then from here to here. That means I can use lower energy photons. And I violate this. Other one, I will not go into too much detail, but here again is the one electron hole pair. If I down convert from one photon two, which can be done nowadays in organics with singlet fission, I will violate this. And then the thermalization of having T cell equals T ambient can be violated in a hot carrier cell when I find a way to use this extra energy that generally gets lost as thermal energy. So there are various ways, and this is a very active area of research. At the moment, nearly all, I would say, except for the multi-junctions, is academic research. Now we can compare the voltage that I can get out to the band gap of various solar cells. And I would like to get all of the band gap out, but that is not possible. I've already shown you what are the various causes for limitations. And I can calculate this formula to take into account the Carnot efficiency and the étendue losses to say that this is where my efficiency is when, if I had a completely ideal cell. And here's gallium arsenide in terms of its voltage efficiency is very close to that. And the nice thing about the halide perovskite is that they're also getting close to it, at least in small cells. And the rest is quite far away, and we have all, generally, the only exception is gallium indium phosphide. By the way, this is logarithmic from 1 to 1/10, and then to 1,000. So you very quickly go to a situation where you can't measure the luminescence anymore. Therefore, it's not really true that a good solar cell is a good emitter. It's an excellent solar cell has to be an excellent emitter. And the moment it's not excellent, you shouldn't use this. So here's the reciprocity between the electroluminescence and the photoconversion efficiency in general, between various types of solar cells. And here's the gallium arsenide, and the perovskite has gotten even a little bit higher since this plot was made. This idea, which has been popularized and based by Ilya Jablonowicz, goes back to the works of Ross, who was a graduate student of Melvin Calvin. Any graduate student listening, there are 2 papers in Journal of Applied Physics of Ross while he was a graduate student, single author, and these people. So, but is it really for open circuit that matters for us? We love the open circuit because it's much easier than nearly any other of the properties of the solar cell to relate to fundamental properties. But it's not really that, because we don't convert any power at open circuit. This is where we want to focus on, and that's the maximum power, voltage, and current. So you can make this plot, which I owe to my colleague Ron below, or at least the basis for it, and you calculate what will be, according to Shockley-Queisser, the minimal loss that I'll get if I compare the band gap photon energy and that of the voltage at maximum power, which I then have to multiply by the electric charge. And you see there are 2 that are very close, gallium indium phosphide and gallium arsenide. So we're now not at open circuit, here at maximum power, which is where the cell really matters for us. And you see it's all over. And there's this disturbing line that suggests that as your band gap goes up, your losses go up. But luckily, there's gallium indium phosphide that saves the day. And here's perovskite. And that's why there's such an enormous excitement about perovskite, because it's a cell, a relatively new cell, that in maximum power is closer to, at high band gap, relatively high band gap, to this minimum, theoretical minimum loss that we can't do anything about in a single cell than any of these others. Now here's amorphous silicon, here's photosynthesis. And there is something that's not entirely fair, because it was shown in the 80s that if you have a disordered system, statically disordered, like amorphous silicon will be, and photosynthesis is, then you lose about this amount of voltage to start with. Doesn't help me for practice, but for fundamental understanding, it's important to take it into account. So let's look later, we'll go back to this, at what's happening here. But first, the halide perovskites. And yes, they've been amazing. if you look at solar cell efficiencies of various types of non-silicon gallium arsenide, CIGS, cadmium telluride, the commercial or near commercial solar cells like the 3.5s, and 2000, and we'll stop at 2013 or so. You see, this is the high sensitized solar cell, and it's reigning over all the others. Now, to put things in perspective, the commercial cells have efficiencies in this band. That's what you can buy on the market if you are in the business of putting up cells on the roof or for a solar cell station. And that is what happens from here to here. Green is halide perovskite. Organics, they have done amazingly well. They're here, where these are the efficiencies that are less than 1 centimeter squared. And then there's also an impressive advance in quantum dot solar cells, but it has to do with that now the quantum dot solar cells are made out of halide perovskites instead of lecture coordinate. But you see, for the first time, these types of cells are getting into the band of where commercial efficiencies, commercial cells are performing. And that leads directly to one of the ways to violating an assumption, which is the multi-junctions. They are called tandem solar cells. And the halide perovskites have been used have been investigated intensively for the tandem cells, even if the articles that draw the attention are for the single junction cells, which would compete with silicon, which is not really going to work in the near future, is my opinion. So instead, a big effort has been on making silicon and halide perovskite, or copper indium gallium selenide, which has a small band gap, and halide perovskite. Silicon has a small band gap. And the best result is here from the Helmholtz in Berlin, nearly 30%. That has been achieved early this year. Now, let's put it in perspective. This is the best halide perovskites, copper and gallium selenide, silicon, and gallium arsenide. It's the first time that the silicon halide perovskite exceeds the best gallium arsenide cell. Here already was a milestone when the silicon halide perovskite tandem exceeded the efficiency of a single junction silicon cell. Now, where are the tandem cells that are readily available? And it doesn't matter if you use silicon or another 3.5, generally another alloy. They're both at about 33%. So this is the gap that has to be bridged, and maybe not all of it, but because supposedly a silicon and a perovskite cell will be much cheaper than a gallium phosphate cell. It gives you an idea. And now look at the development of the halide perovskite efficiencies. And the band gap has changed because of alloying. And you see a disturbing thing. And in the quest to get the best single junction solar cell efficiency in order to get your article into that journal, in terms of what we need for tandems, has been a trend in the wrong direction. And that has definitely delayed the development of the tandem cells. So we'll skip this because I want to get to others. So the deviations from the ideal Shockley-Queisser performance for various types of solar cells, where the red is the current and the green is the voltage, and the brown-orange is essentially what gives you a deviation from ideal diode behavior. And what you see, the fill factor, is that for gallium arsenide, it's the current that is the main problem. For silicon, that's not the case. And for silicon, it's the voltage, and you can understand it. It's an indirect semiconductor. Nothing you can do about it. For cadmium telluride selenide, which is a commercial cell, it has 7% of the world market. Yes. It's definitely the voltage. For halide perovskites, it's neither. It is this problem of the diode factor, and it can directly be traced to something that we pointed out several years ago in a chemical review, that it's all about interfaces. And that's nothing new. For anyone who has worked on materials, you know that the surfaces and the interfaces deserve special attention. So let's skip that. Now, how are the technologies developing? And the commercial module is here in purple. So gallium arsenide doesn't have a real commercial one, but there are various silicon technologies, and silicon is such a mature technology that it has a very well-established roadmap. They know what they're going to do until 2030 and probably 2035. They already have tested everything, and now they only have to make sure that the tools are ready. So this is the gap between the best cell and the commercial module. And you see the mini and the standard cell have no difference for silicon. Also not for CIGS. For catalyte, the mini cell is a bit more efficient. For perovskite, there's a big gap, as for the OPV, although relatively speaking less. And then what about the modules in the lab? We have only modules in the lab here. They're way behind this black one. The black one is what gets the headlines. So it gives you an idea of where industry is today, and CIGS has only a very small market share, and you can see why, because it hasn't been able to really keep up with telluride. And that is where the perovskites have a chance, and the OPV will also have a chance if they can get that they can reduce this gap. Stability. So here are the perovskites. These were considered unstable, telluride and CIGS. At the moment, at high efficiencies, they are stable as silicon. So the perovskites have to work on the stability. And this is what was done with commercial cells, and you get an idea of the degradation rate per year. There is degradation, but they are guaranteed for 25 years, sometimes 30 years. This is the manufacturer guarantee of solar power, now a Total company, for SunPower. For some reason that only the manufacturers and the industry knows, they sell you something at 100 watt, but they guarantee you only 95 watt from day one. It's a little bit like you buy a new car, and the moment you drive it out of the showroom, it loses its value. So that is, but in the end, it's guaranteed to stay above 85% of its original efficiency for 25 years. And that leads...
David, sorry to interrupt. We need to finish up soon, so people have also time for some questions.
Okay, so I'll go on. This is where solar cell powers are today. As of now, we have more than 0.9 terawatt peak installed. Peak means that you have to divide by about 5 to get the equivalent continuous power. The world power use today is about 18 terawatt. Puts it in perspective. If you take the largest solar power PV plant in the world, for getting 4 terawatt continuous, just from PV would require to put 2 such plants a day for 14 years, naturally plus storage. That's something that at the moment only the People's Republic of China would be capable of doing if they would want to. So my conclusions are that silicon is here to stay for quite a while, but we have to, or the industry has to find ways to decrease the cost per watt. In terms of what may happen in the future, just never say never. And yes, PV alone won't do it, but also batteries alone will not be able to keep up with PV plus wind. We'll need a mix of storage, which sometimes is forgotten. Thank you.
Thank you very much, David. That was really interesting. If anyone has any questions, please raise your hand or unmute yourselves. I don't see any raised hands. You can also type if you can't talk, and I will read the question out. Yes, Chagai.
Hi, David. Thank you for the excellent talk. Very interesting. So if perovskites are so promising and they have only this problem of stability, you think that this could be solved on what level? I mean, could this be solved on the packaging level, on the material side?
It's two ways. The encapsulation is critical, but I think the technology exists because the dye-sensitized solar cells were sold commercially at some point with encapsulation. That's a much harder task than encapsulating the perovskites. And the second thing is that, yes, the surfaces and interfaces are their Achilles heel, like everywhere. In silicon and gallium arsenide, it took decades to tame their surfaces and interfaces. But we want Mashiach now, and that's not going to happen.
Any more questions? I hear someone else is unmuted or raising their hand. I think people have to take some time to have this sink in, but I do have one question. You mentioned in the beginning of your talk about the silicon having this 99, almost close to 99% efficiency with regards to the uptake, but I think the question
with respect to the current.
Yeah. So I think for me, the question is, why is this the case for silicon if it's an indirect bandgap material? I mean, it's so much harder to convert these photons.
No, because silicon, carriers in silicon have a very long lifetime, and therefore they can travel a long distance. So you can make relatively, and you have to make also for absorbing the light, a relatively thick cell. And this allows for, and nowadays they are thinner, but with a reflective back surface. And so that's how you can get to this efficiency. The other cells are much thinner, and carrier lifetime and carrier diffusion length is much less.
Thank you. Adi, I see you have a question.
Yes. Hi, David. A very nice talk. I have a question regarding because all environments, all the solar cells are better, basically are done to make our life better. So in terms of environmental risk, pollution, and so on, what is the recommendation, or what is out, what is in? Like maybe we stay only with silicon and that's all? And also another question regarding the hot electrons, but this you can answer.
Okay, 1 minute. So with respect to the environmental impact, yes, it is a major problem and only addressed by cadmium telluride because it so obviously has poisonous material. And so cadmium telluride is sold. Only recently it has been started to be put on roofs because people didn't want it. And it has a lifetime guarantee back that at the end of the life, the company will take it back, guarantee, supposedly to reuse the materials. By the way, the company has an interest in doing that because tellurium is about as rare as gold and platinum. But that's the only way. Silicon at the moment, silicon cells are made to be as efficient as possible with the solder that's needed. Many of those cells still have lead in the solder, and they are not designed even for easy recycling. This is now something that is starting to catch on, but since you know who's the main producer, it is difficult at this point to start making an impact. But it is a big problem, although much less so than actually with other electronics, because the solar cell is a relatively simple electronic device.
And okay, thank you. And regarding so it seems like hot electrons can solve some of the problems like the efficiency and so on. So if you can.
So yes, the problem is that
hot carriers.
You have to find contact that will allow you to preserve the extra energy that you're not losing. At the moment, the main contact to a solar cell is aligned to the conduction band and the valence band in order to minimize the energy loss. But now, if I have so it's here. Now, if I have a system where I found a way to preserve the carrier hot, I have to have a contact to take it out. And that is a problem that is very difficult to solve. But it's not impossible. I do not know the solution, but it should be possible. You need a very selective contact.
Okay. You need to preserve it. It's not enough to have a plasmonic electrode as a contact to.
It has to be a contact. It has to be a contact at which the electron free energy is preserved and can be put into an external circuit. And that circuit probably should be separate of the main circuit because it has a higher voltage. And the moment you mix them, you lose that energy. So the problem is, let's assume we found a way to collect it. How can we preserve that extra free energy so that it will be translated into the voltage that we take out? If we just put at the end all of the electrons together, we are going to the lowest common denominator. And this is the challenge that people are trying to address. And it's not impossible. And the example for me is that until 3 weeks ago, you would have told me intermediate gap solar cells, and I would have laughed out loud. And then suddenly it comes with a system for something completely different, and it stares at you. There is a system that will be possible. So here, it may have to do with very smart material engineering after you solve the problem of preserving, which can be done with plasmonics, yes.
Great. I don't see any more questions, and we're a little over time. So thank you again, David. Just one word from Shoshana Dan from Ben Gurion University, who would very much like to advertise the 23rd Stable Symposium for Solar Electricity and Production. So anyone in the field, of course, related to this talk is more than welcome to look it up and sign up. Thank you again, David, and thank you everyone for attending.